Okay, we're on question 7, which is the last question on the differential equation worksheet. So question 7 says, dy dx is 1 over y plus x squared y, and we have an initial condition y of 0 equals 2. We are looking for an equation for y in terms of x, which means we need one equation. It is not the only equation because we're going to end up using a periodic function as a solution to this, which means it's going to repeat itself forever. So we're just looking for one way to solve this problem. So what we're going to do to start this guy out is we have to separate our variables. And it's too complex to separate them all at once right now. So what I'm going to do is I'm going to cross multiply. That's going to be my first jump here. It is possible to skip that step and go straight to separating direct variables with some factoring, but that's going to be, we're getting kind of ahead of ourselves there. So I'm just going to break it down into each step. So we're going to start by cross multiplying. I'm going to end up with y plus x squared y equals dx. And I can't get the x away from this y until I deal with the fact that I've got these two different things on the left being added together. So I can't just pull out this x, because I'll have to pull out an x from here as well, but it doesn't have an x in it, so that's not going to work out. So instead, what I have to do is find a way to separate the y's and the x on the left, just focusing on the left. Now, what I notice is that y is in both terms. One y here, one y here, which means I can take that y and pull it to the front. I can factor it out. It's a common term. So if I take y out of itself, I just have 1 left over. And if I take y out of x squared y, I just have x squared left. So I've divided both terms by y to factor it out to the front. I've like undistributed it. We still have dx left on the right. And now we can see that in order to get the 1 plus x squared away from y, now we can just divide both sides by 1 plus x squared. So on the left, we will have, oh, I forgot to write my dy. Why didn't you say anything? Probably because it's a video and you can't tell me things. Probably going, Miss Purvis, you forgot to write your dy. Okay, here we go. So we're going to divide both sides by 1 plus x squared, and we're going to end up with y dy on the left. And on the right, we're going to have dx over 1 plus x squared. Cool. When we go to integrate this, we can integrate both sides. The left side we can do. The integral of y dy, we use that power rule that we know. We just raise its exponent by 1, divide by that new number. We got this. On the right, this is not something that I can integrate using u substitution. This is not something I can integrate using the power rule. I do not have a quotient rule. This is an identity. If I rewrite this just a little bit, I'm hoping it will ring a bell. This is 1 over 1 plus x squared times dx. This identity is the derivative of an inverse trig function. So you have to remember your inverse trig derivatives in order to finish solving this problem. The inverse trig function that gives us this derivative is tangent. So this is, when I integrate it, this is going to give me the inverse tangent of whatever was being squared. So that's x. So this is going to be something that's helpful to study. One of the ways that I remember that this is tangent, all of the other inverse trig derivatives have square root symbols in them except for tangent and cotangent. And if you recall the trig derivatives themselves for regular trig functions, not inverse ones, tangent and cotangent are the only ones that have a derivative that is being squared. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So if you think about tangent and cotangent as having squared derivatives, then it kind of follows that the inverse tangent and inverse cotangent would have the only derivatives that aren't being square rooted, because we can think of them as already having been squared. So that's one of the ways that I remember that if I don't see a square root sign and it looks like this identity, it must be tangent. Okay? If it was negative, it would be cotangent. Okay, so we have our function here integrated. We can put our plus c on the end. We are almost there, except we have to use our initial condition. So there are various ways to go about this. One of them is to multiply everything by 2 first. I'm going to go ahead and leave it just as it is so we can see what happens if we just look at this as it stands right now without getting rid of our fraction first. But there are many, many solutions to this problem. So if you get to this point and then continue on, I don't think it would be incorrect to multiply by 2 first and then solve or whatever have you. So we're going to plug in our 0 for x, and we're going to plug in our 2 for y. So over here, I'm going to end up with 2 squared over 2. That's going to give me 4 over 2, which is just 2. And inside here, I'm going to have the inverse tangent of 0 plus c. So the inverse tangent of 0. Inverse functions are designed to tell me what the input of a regular function would have been. So if I have f of x and I plug in an x and it spits out a y value, if I'm looking at an inverse function, I'm not plugging in an x value. I'm actually taking this answer, plugging it back in, and it's spitting back out the x value. It's designed to undo everything my original function did. So the inverse tangent is designed to tell me what I plugged into tangent to give me that number. So let's take a look at it this way. The tangent of some number is going to give me 0 because my inverse tangent of 0 is going to give me that number. So I'm going to call it q just for fun. So whatever this number is, whatever q is that I plug into tangent that gives me 0, that's what my inverse tangent is going to spit back out. So if I'm looking for this q, what I'm really looking for is some number inside of tangent that will give me 0 as an answer. So let's take another look at our unit circle to figure out how to find this. The unit circle will help you with this. It may not be immediately obvious, but our unit circle, let's fill in those points again. We had over here 1, 0, that was at 0. At pi, we had -1, 0. At pi over 2, we had 0, 1. And down here at 3 pi over 2, we had 0, -1, right? 0, pi, pi over 2, and 3 pi over 2. And this we used in the last video. So if you're stuck on that one, just go back and rewatch that. Okay, so this unit circle, these coordinates that we found so far, they are designed to tell us cosine and sine values. They don't say anything about tangent. So it is important to remember that the tangent of a number, like x, the tangent of x is the sine of x divided by the cosine of x. This is one of the first identities that you would have learned in trigonometry. So the tangent is sine divided by cosine. I want to find out when my tangent is 0. So I want to find out when sine divided by cosine is 0. So if I have a 0 for sine and I divide it by cosine, I will get 0 as an answer. If I have 0 for cosine and it's on the bottom of my fraction, my actual answer will be undefined. So I don't want to worry about when cosine is 0. Cosine of 0, cosine of x equals 0, this is going to be undefined for tangent. What I'm looking for is when the numerator of my fraction is 0, because if I divide 0 by anything, it's going to give me 0 as an answer. So what I'm actually looking for on my unit circle is all the places where sine of my angle give me 0 as an answer. And remember, sine comes from my y value. So this is sine here, 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 and here. So I want to find the places where my sine gives me 0. And that happens right here on the x-axis. The sine of pi is 0. The sine of 0 is 0. And this technically keeps going forever. This is a periodic function. It repeats forever. So the sine of pi is 0. The sine of 2 pi is 0. The sine of 3 pi, 4 pi, 5 pi, -16 pi. It doesn't matter which way I go. If it's on this axis, the sine is 0. So I just have to pick one of those values to find an equation. That's why this doesn't say find the solution, because there's infinite solutions. So the easiest one to pick is that one right there, the number 0. If I plug 0 into tangent, it's going to give me 0 as an answer. So that's awesome. Up here, the inverse tangent of 0 could be 0. So we're going to say 2 equals 0 plus c. Okay? So that means c is going to be 2 in this case. There are infinite solutions. This is one of them. If that's the case, then y squared over 2 equals the inverse tangent of x plus 2, because c is 2. All I have to do to finish solving this equation is multiply both sides by 2 and then square root. So let's go ahead and multiply both sides by 2. Y squared is going to be 2 times the inverse tangent of x plus 4, because I'm going to multiply everything by 2. Then finally, I'm going to square root both sides. And my final answer is going to be y equals the square root 2 times the inverse tangent of x plus 4. That's it. That's my particular solution. I could have picked any other values over here. I could have picked pi. I could have picked 2 pi, 3 pi, any of those numbers to plug in here, and it would have changed my value for c, and it would have changed my final answer. The other thing is I could have multiplied by 2 first, and it would have changed my answer a little bit as well. But like I said before, there are infinite solutions to this problem. So it's the process itself of finding the inverse tangent by looking at tangent, of finding the sine and cosine values in the function, and most importantly, by recognizing an inverse trig derivative so that we could integrate it. Those are the things that I really want you to focus on. Feel free to ask me questions in class about any of this, and I'll see you guys at school.